So buffers, they are all over the place. We've been spending a lot of time on pH. What's the pH of this solution? What's the pH of that solution? Well, pH is a big deal, and since it's so important, if it's working, right, with like in the environment, if the little fishies are nice and happy, well, it'd be nice for the pH to stay there. Well, one way for it to stay there is for in the environment, just naturally, for there to be a buffer. A chemical system that's going to, ooh, we get some acid rain. Hey, the pH stays roughly the same in the lake. Ooh, we get someone dumps in Drano into the lake. Ooh, the pH stays roughly the same. It could be in mining, making fertilizer, growing stuff. You want pH not to change very much, and buffers are going to help you do that. I don't know, what is this, Bud versus Coke? Coke has phosphoric acid, increases the acidity. Your body buffers it, but then your teeth get leached. Okay, and then versus beer, well, beer is probably worse, right? You get addicted and things. But so if your pH gets outside, above or below a certain range, you can not kind of lose your smarts there. So the idea is inside your system, there's a buffer inside your blood. And the backbone of why this works is really the common ion effect. And if you have reactants going to products, right? And all the common ion effect is if you add one of the products, Albert, the equilibrium shifts where? Towards the reactants. If you add a reactant, well, then it shifts towards the products. That's Le Chatelier's principle, right? So that's kind of really what's going on. But the ionization reaction for the acid HCN, Jasmine, how would we write that reaction? I call it the Ka reaction, but HCN
plus H2O.
Well, that's the Kb reaction. Just the Ka reaction, HCN goes to
So I'll go to
H plus and
C, yeah,
perfect, right? There's the Ka reaction, the ionization reaction of HCN, cyanic acid. AJ, let's assume that this is at equilibrium. Everything's hunky-dory. All the concentrations aren't changing over time. They're nice and steady. What would happen to the total moles of H plus? Would we get more or less? If more HCN is added, would you have more H plus or less H plus? More. Everybody agree? Yeah. You're adding, you have too much reactants, so it's going to shift products. We had some sodium cyanide solid, Monica Lopez, to the solution. It's kind of missing. This might help, might not. I don't know. Our little AQs on there. So here's the question. If you don't remember the solubility rules, then you would look at, for this common ion effect game, sodium cyanide, solid. You look for, first it's a solid, so it can't really affect anything, right? And then it's not up here either, but no. There's only one way to add cyanide. You can't just get a bottle off the shelf and add cyanide. You can't do it. It's impossible. It's like having half a battery terminal. You always have to have a plus and a minus. You can't have just one terminal and have it be a working system. The only way to get that into solution is to add a cation to it that's going to make it dissolve. So that's why I crossed out the sodium. Every single time in my brain, I don't see sodium. I don't see what other ions? Lithium. And I don't see potassium. They never do anything, right? And in previous class, a student called them stand-ins. Perfect. They don't do anything, just stand-ins to get the cyanide in there. So really what we're adding is cyanide. So what happens to the H plus? It's going to be less. Exactly. Because it's now we have too much product. It's going to shift to reactants. Okay, that's kind of what's buffers. Alyssa, a buffer is a solution that has the ability to resist slight changes in what? When small amounts of an acid or a base is added. pH. Right. All blanks, Lauren, are mixtures of a conjugate acid and a conjugate base. All buffers. Okay. In fact, Albert, any solution of a blank acid can be used as a buffer. The answer is weak. He's right. Do you see why? Right? If you pick the answer strong, well, hang on. The idea of let's back up a little bit. The big picture is you have a buffer. That means you have to have in that buffer a conjugate acid and a conjugate base. Otherwise, it's not a buffer. Okay, so why? Well, you have some conjugate acid there in case you add some what? To keep the pH the same. You add some base. You dump some base in there. You don't want the pH to change. Well, then something darn well better react with that base. The conjugate acid does. Fine. You've got a buffer system. You're going to dump some acid in there. Well, then there's a what in that buffer to react with that acid? A conjugate base. There has to be both. If you pick the answer strong acid, well, you've got plenty of acid, but you don't have any conjugate base. So you dump in acid, it's going to get even more acidic. So this is not a buffer system because I don't have appreciable amounts, right, that are going to work. That conjugate base doesn't do anything in a strong acid. He does nothing. So that's why the only answer is weak. You need conjugate acid and conjugate base. They both work. Conjugate acid reacts with the base, and the conjugate base reacts with an acid. That's really how this whole pH thing stays constant in a buffer. Okay. Eric, it says that this is a buffer system. What makes that a buffer system? You see a what? You see a conjugate acid and a conjugate base. Or even a better answer, you see a weak acid. Because you could write a strong acid dissociation reaction, and I see a conjugate acid and conjugate base, but the conjugate base is worthless. He's another stand-in. Okay. So that's a buffer system because there's a weak acid. Victoria, in this system, the conjugate acid present is HF. And everybody, the conjugate base is F minus. Okay? If any acid, Ramiro, any acid, and the book is going to dump, we're going to have these buffer systems, and they're going to add some acid, they're going to add some base to these buffers, and every single time the acid's going to be a strong acid, and every single time the base is going to be a strong base. So the word any is kind of not really true, but it actually works though. In the homework you're going to see strong acid. But anyway, what am I asking you? I'm asking you if any acid, and the homework's going to be strong acid, is added to a buffer, to this buffer in particular, what will react with it? The F minus. Does everybody agree? He's right. Because HF is an acid. An acid can't react with an acid. So you dumped in a bunch of acid in this buffer, something better react with it. Otherwise the pH is going to drop like a rock. If something doesn't react with it, the pH is going to drop like a rock. It's not a buffered system. Something has to react with it. The F minus does. Okay. So Mari, well, if the F minus reacts, do you agree? So what does it turn into? F minus reacts and produces HF. It really follows this. Right? Here's the added acid. Right? You dump in way too much of it, F minus is going to react with it and form HF. Get rid of that excess acid. Okay. However, Jessica, if any base, well, we're going to be adding strong bases. If a strong base is added, what will react? The HF, the conjugate acid, will react. Okay. The conjugate acid reacts, Vanessa, and it's going to produce F minus, which also keeps the pH relatively constant. So we don't have that reaction up here, right? You'd pretty much have to write it. HF plus OH minus, right? And pick water and F minus. See what I'm saying? I don't think this is more than you need to know, but this is what would happen. Right? It would produce the F minus. Okay. C. 250 mils, Maria, of 0.1 molar HCl is added to this buffer. Then the number of moles of F minus would what? Increase? Decrease. Yeah. Because that F minus has to react. F minus has to react. So otherwise that pH is going to drop like a rock. So something better react with that HCl.
So it doesn't matter if they're the same type of acid? They can still...
It's always going to be a strong acid. And here's the reason why to answer this question. It's always a strong acid or a strong base they're adding. Always, always, always. Okay? So why? To answer this question, to fill in this blank. So everyone agrees you add an acid, F minus reacts, so its amount decreases by how many moles? You're so close.
Oh no, do you divide?
Right? This is, I got to do the math, right? You remember the equation we set up to get the moles? What we're after is getting the moles of H plus. Because for every 1 mole of H plus that reacts, how many moles of F minus? So for every 1 mole of H plus that you add, how many moles of F minus are going to react? For every 1 mole of H plus you add, you're going to have 1 mole of F minus react. It's kind of right here, right? It's 1 to 1. It's 1 to 1. So if you add 1 mole of H plus, 1 mole of F minus reacts. Well, how many moles of H plus did we add? Right? Do you remember the big M was what over what? Moles over liters. That's the algebraic equation we set up. So we have 0.1 has to equal moles over how many liters? 0.25. So my moles should be 0.025 then, right? This is going to be 0.025. That's why it's always a strong acid. So you can figure out exactly how many moles of H plus or however many moles of OH minus you added if it's a strong base. Okay, so we add HCl, so many moles of it, 0.025 moles of it to be exact. F minus reacts. It decreases by 0.025 moles because it had to react with all that H plus. And the number of moles of HF will increase by, do you follow? 0.025, exactly. Very good. Okay. So you had 1 mole of H plus, 1 mole of F minus would react, 1 mole of HF would form. All that just to keep the pH relatively the same. Okay. But the pH is going to change a little bit. Can't help it. If you add some acid, the pH is going to go down, but just a little bit if it's a buffer. So how do you predict just how much that pH is going to go down, or what's going to be the new pH? Henderson-Hasselbalch. This really came from ice. But let's just skip all that and just use his equation. In fact, I want to use this equation. This one is really his true Henderson-Hasselbalch. But I like this one. I think it's easier. What changed in going from the one we're supposed to use Concentration is what over what? Moles over liters. So this one, I canceled the liters. Why? Is the conjugate base and in the conjugate acid, are they all in the same beaker? Yeah, they have the same volume. So every single time, volume will cancel out on you. So it's so much easier. Okay, so we calculate the moles of conjugate base divided by the moles of the conjugate acid. Whatever's there, you got to tell you. Take the log of it, add something called pKa, and you get the pH of the buffer. So whenever there's a buffer problem, right? Problem can be as complicated as you want, but they have the word buffer in it. I can guarantee you, you're going to be using this equation. Okay, let's jump down and see what a Ka. Ka is 4.9 times 10 to the negative 10. 4.9 times 10 to the negative 10. Isn't that what I said? Yeah, 4.9 times 10 to the negative 10. If that's what Ka is, what's pKa? Oh, I bet Brandy knows. No? I'll give you a hint. pH is the negative log of H. pKa, yeah, negative log of K. So you knew what it was. pKa is a negative log of Ka. Negative log of 4.9 times 10 to the negative 10. Let's see, what would that be? We're going to need it for the next problem anyway. 4.9 times 10 to the 10 negative. Got to take the log of it, and then I have to take it times a negative 1. So I get 9.31. Make sure that works for you. 9.31. We good? A buffer is prepared by adding 50 mils of 0.25 molar sodium cyanide to 40 mils of 0.2 molar hydrogen cyanide. What's the pH of the final buffer solution? Okay, Summer. How are you going to start with this thing? Oh, she got the easy one, right? We already found the pKa. So, you know, she knows we're going to use this equation. And she said, find the pKa, that 9.31. Right? Okay, I'd say, Jasmine, the easy stuff is done. So what can you do now? We're after that pH. Find the moles of which one? Okay, moles of the conjugate base, AJ. How are you going to do that? Which one is it? All right. She wants this one. So is that the sodium cyanide or the HCN? Sodium cyanide. What's the sodium doing there? Again, just get rid of it. It's a stand-in. Doesn't do anything. So we need to get moles of it. Monica Lopez, what equation you set up to get the moles of it? Yeah, big M is moles over liters. Big M is 0.25. Liters is 50 mils. Alyssa is how many liters? 0.05. Move it over 3 places. 0.05. 0.25 times 0.05. About 0.0125. Okay. Then we got to do the same thing for the, so this is the moles of cyanide. Let's get the moles of HCN. Do the same thing. Calculate the moles of HCN. Substitute it into our modified Henderson-Hasselbalch equation. Should get the pH. Of that buffer you just made. Anybody get an answer? 9.5? 9.5? Give it maybe to the hundredths place. What is it to the hundredths place? Because I don't know if cause there's a part B and the pH is going to change on us. You get a 0? Okay. I don't know how much it's going to change because I know because you know what's coming up. They're going to add some strong acid or some strong base. So let's see, what is it going to be here? What is the pH if 100 mils of 0.01 molar HCl is added to the entire buffer solution?
So you put that to the conjugate base.
Okay, we're getting there. We're adding acid. So the moles of the conjugate base, because that's what has to react with this acid? The conjugate base. Okay, we really don't even care what its identity is. You just know the moles of the conjugate base are going to react. The moles of the conjugate base is going to go down. The moles of the conjugate acid is going to go up. So I say you totally just copy this equation, right, and put plus and minus in the right spot. Then you figure out what to do. See what I'm saying? I say you copy this equation because you already did so much of this work. Plus the log. We have 0.0125 all over 0.008. Okay. On the top, is it 0.0125? Is it a plus or a minus? It's it's minus, right? Because the moles of base has to go down. Remember? Its base is up on top. So that one has to go down. So let's put minus. The conjugate acid, that's on the bottom. That one formed. So that one will be a plus. So I say this is what you do. And then you start thinking about it. All right? And starting with the numbers.
So will it be the same number for both?
Will it be the same number for both? Do you agree? Yes, it will be. And what will be that number? Is it going to be the... It's going to be the moles of the H. What volume do you use in that equation, right? To get the moles, we like to use this equation, right? Big M is moles over liters. I think everybody agrees that big M is 0.01, though, right? What are you going to use for the liters? Yeah, convert it into liters. Is it 0.1 or is it? Look at all these other liters too, though.
No, you're just using because that's the new added.
Exactly. You want the moles of H plus So you just care about this volume right here, the volume of the H plus that you took. Right, so that's 0.1. Good. Solve for that. Solve for that moles, and that's the number you're going to put in. That's the number you're going to put in right here. That'd be 0.001. And that's what you stick in. I'm going to write some intermediate steps here to make sure you're doing it right on your calculator. Okay. So it's the log of this entire quantity. So you have to take 0.0125 minus 0.001. And what you could do is hit divide, then use the parentheses on the calculator if you want to do it all in one big step. Divide by, in parentheses, 0.008 plus 0.001, close the parentheses, or just write down the different numbers. But regardless, you should get 1.28 inside that log. Take the log of it, add it to 9.31, you get 9.42. Ramiro, did you get 9.42? Okay. So Mari, does the 9.42 number make sense? In other words, it was 9.5. Does it make sense that it's now 9.42? What I'm getting at is the pH changed only a little bit, so that's a good sign, because it should only change a little tiny bit. So that's a good sign. But did it change a little bit in the right direction? It's more acidic or basic now? It's more acidic. It's more acidic, and that it should get more acidic because you just added some strong acid. So the solution should get more acidic, but only a little bit. So the number makes sense. Okay. Alrighty then. Try this one. Try this one. If you're not sure, just ask. Just try to get A before we go on and do B. See if we can all agree on A. What'd you get for your pKa? 7.46. Did you get 7.46? 7.42? No, it's going to be the negative log of this thing, right? Okay. Ramiro, what did you get for moles of conjugate base? 0.18. Did you get 0.18 about? Okay. How about moles of conjugate acid? Jessica, what did you get for moles of conjugate acid? For the bottom part. We're down here. 2.7? Anybody else get 2.46? 0.246? You see where they're getting that, Jessica? They're setting up, here's their acid. So 0.82 acid moles all over 0.3, right? So you take 0.82 times 0.3, you get 0.246. Okay? And then the final answer is 7.34? Okay, anybody having trouble with that one? Just this part A. Lauren, you got 7.34? Okay, well. All right, well, that should be close. All right. Now, these buffer problems, I would carry 3-4 digits the whole way through at least. Otherwise, your answers aren't going to agree with the back of the book. Okay? And the reason why I want us all to go on to step B together is it's kind of a trick question. Okay. So, Brandy, you get 7.34? Okay. Let's see what the trick question is here. What's the complication in part B? Yeah, they're only adding it to 100 mils of the buffer. Before, right, didn't we just, I said, hey, let's rewrite the equation, right? pH equals 7.46 plus the log, right? And then you just copy these numbers in. Remember doing this? And then you put a plus and a minus in somewhere, right? We can do the plus and the minus part if you want. We're adding an acid. So that means the conjugate acid or the conjugate base is going to react. Conjugate base, and that's on the top or the bottom? The top. So we should put a minus sign. Okay. So this negative or negative, same thing. This is where I was saying to start. But like Jasmine said, you don't have 0.1875 moles of conjugate base to start with because you're not using, the total volume is what, 300 plus 250 is like 550 mils. You have 550 mils of buffer. But you didn't use all 550 mils. You only took out 100 of it. So this 0.1875 number is wrong. This 0.246 number is wrong. They're both too big. So how are you going to fix it? No, it'd make it a lot easier if let's say, just pretend the number wasn't 550. The number is, what's an easier number to do math? 600. And they used 300. Then you use exactly how much of the buffer, what fraction? A half. So then you take 0.1875 times a half, take 0.246 times a half. Nothing changes then. You just put in your fraction that you used. We have to do the same thing. except our fraction isn't a half. Our fraction is going to be what over what? 100 over 550. 100 over 550. That's our fraction. Now you can figure out what that fraction is and just stick it down here, or write the fraction there. 100 over 550 times 0.1875. 100 over 550 times 0.246, which is what I'm going to do because I don't want to skip any steps. 100 over 550 times that. 100 over 550. Okay. Nothing else changed. We just have to reduce our initial moles of conjugate base and conjugate acid because they're way too high. So there's going to be some homework questions like that. They're only going to add it to part of the buffer. I think there's maybe one, but now you're ready for it. We still got to figure in what number to put here. All right, that number, we got to figure out what that is. How do you do that? How do you do that? Victoria, how do you do that part? No. We're trying to... Yeah, we're going to use these two. Because we want to figure out the moles of the strong acid or the moles of the strong base we added. Yeah. Not 0.35. It's going to be this. Big M is moles over liters. She's right, though. 0.35 has to equal the moles. Let's see. 25 mils is going to be 0.025. You're on track. Good. Oh, shoot. 8.75 times 10 to the negative 3. So that's the number we stick up here. Okay. And hopefully, we'll get a number that's just a little bit smaller than 7.34. If you did, you're doing it right. Or it could be. Has to come out smaller, otherwise something's messed up. Right? 'Cause you're adding an acid. And it might be kind of a bigger change because we don't have as much buffer there. Right? The capacity has gone down because we don't have as much moles of conjugate base and moles of conjugate acid to work with. We're not working with the full 550 milliliters. So it might drop down a little more than usual from 7.34. Let's see. You got 7.14? Oh yeah, a lot of people got 7.14s in the answers. I bet you that's it. So it dropped down a couple decimal points there. Here, let's, for you folks who got 7.14, log, what's on top? What's your top number? 0.0253? Just so that folks can, and what's your bottom one? 0.00? 0.0535. Okay. And then that should work out for you. Okay. Oh, we went over. We are out of time.